Okay, so our today's topic in waves in AS physics is waveforms and some terms related to them. So the first term is phase. Phase. So the state of the vibrating particle with respect to its mean position is known as phase. You know, when there is no wave in the medium, then all the particles are resting on its mean position. But as soon as a disturbance or a wave passes through it, all the particles are displaced from their mean position and they start vibrating up and down. They start oscillating. So phase is actually the state of vibrating particle with respect to their mean position. So what are the things that can determine phase? There are three things. One is the displacement from the mean position. And you can see particle 1, particle 2, particle 3, and particle 4. All these particles are displaced from their mean position except for the particle 4. And they have different displacements. Only particle 1 and 3 have same displacement. Second one is speed of vibrating particle. Like if you want to determine the phase of the particle, you have to understand, you have to know three things. What is the displacement of the particle from mean position? What is the speed of vibrating particle? And what is the direction of vibrating particles? So actually there are three things that can determine the phase of a particle: displacement, speed, and direction. Okay. Based on this knowledge, there are two types of particles: in-phase particles and out-of-phase particles. In-phase particles are the one which are lambda apart from each other, one wavelength apart, or its multiple, 2 wavelength, 3 wavelength, 4 wavelength. And in-phase particles have same displacement, they have same speed, and they have same direction of motion or vibration. So in-phase particles are actually the identical particles. For example, all the particles on crest of the wave are all the particles on troughs. So all the particles on crest of a waveform are in phase. Similarly, all the particles on all the troughs of the same waveform are in phase. Out of phase are the particles which are not lambda apart, and the particles don't have common speed, same speed, displacement, or direction of vibration. All neighboring particles in one crest or in one trough are out of phase particles. So if I take you back to the diagram, so you can see that on this diagram from 0 to 12, particles are all labeled with numbers. X-axis can be distance, X-axis can be time, X-axis can be angle in degree or angle in radian. If X-axis is in distance, then you can tell that one wavelength is at particle 8 lambda, and this at particle 4 it is half lambda, at particle 2 it is quarter lambda. If it is time, if X-axis is labeled as time, then quarter of wave is t by 4, half is t by 2, 3t by 4, and one wave is having time period of t. If it is angle, for quarter of wave, it is 90 degree or pi by 2. For half, it is 180 degree or pi. For 3/4, it is 270 or 3 pi by 2. And one full wave, it is 360 or 2 pi radian. Now you can see that the particle 2 and 10, they are in phase. They are in phase particles. Why? Because they have same displacement. Both of them are at rest, and next moment, both of them are going to move downward. So particle 2 and 10 are in phase. Next is, let's say, particle 1 and particle 9. So the 1 and 9, these are in phase particles because they have same displacement, they have same direction of vibration, and they have same speed. The next few particles which can be in phase are number 3 and number 11. Because 3 and 11 are lambda apart. So all the particles which are lambda apart are actually in phase particles. So 1 and 9 are lambda apart, 2 and 10 are lambda apart, 3 and 11 are lambda apart. That's why these are known as in phase particles. The next one is 0 and 8. These are in phase particles because they are lambda apart. The next one is 4 and 12. These are in phase particles because they are lambda apart. And the particles which are out of phase can be 1 and 2, 1 and 3, 1 and 4, 1 and 5, 1 and 6, 1 and 7, 1 and 8. or it can be 2 and 3, 2 and 4, 2 and 0, 2 and 5, 2 and 6, 2 and 7, 2 and 8. It can be 4 and 5, 4 and 6, 4 and 7. Like all the other particles which are not lambda apart are actually out of phase. I hope this is clear. Okay, now the next thing is, what is phase difference? Phase difference, delta phi. The difference in phase angle between two vibrating particles in a medium is known as phase difference. The difference in phase angle between two vibrating particles in a medium. It is measured in terms of angle, that is radian or degree. SI unit for phase difference is radian. A particle goes through 360 or 2 pi radian during its one complete vibration. We know this, that when a particle is vibrating, when like one complete wave passes through it, and that point was P. So this, after passing through one full wave, the particle goes up, down, down, and up. So it completed one full oscillation when one wave passes through it. And the angle that it has gone through is 360 degree or 2 pi radian. The next thing is, let's say you can see the diagram. In the first diagram, there is no vibration, so all the particles are at rest. Particle 1, 2, 3, 4, 5, 6, 7 are at rest. Okay, when the source starts vibrating and 1/4 of the vibration is started, then particle 1 goes up and particle 2 stays. And when half vibration is completed, like the source goes up and down, then half of the wave is completed. When 3/4 of vibrations are being formed, then 3/4 of wave is formed. And when one full vibration is completed, then one full wave is being formed. How this is important, how to find phase difference between particles on a wave or between two different waves in a medium. In same medium. Okay, so phase difference between particles on the same wave. So first we have to see that. So this is like the one wave, and there are many particles on it, like 0, 1, 2, 3, 4, 5, 6, 7. And below it, all the angles are given. Particle 1 is 0, particle 2 is 90 degree, 180 degree, 270, 360, 450, 540. Okay, now what they say is you have to find the phase difference between particles 1 and 2. So the phase difference between particle 1 and 2 is 90 degree. Why? Because 1 is at mean and 2 is at extreme. So it is 90 degree straightforward, or pi by 4. Similarly, between 2 and 3, 3 and 4, 4 and 5. So between every two adjacent particles, the phase difference is pi by 4. And then from 2 to 4 or 1 to 3 or 3 to 5, the phase difference is 180 or pi radian. So how you can find the phase difference between two waves? Two waves. The waves have same wavelength, same frequency, same speed. Okay, so let's say this is the first wave. And let me draw the second wave. This is the second wave. X-axis is distance, y-axis is displacement. So what you have to do is you have to find the phase difference between them. Okay, as you can see, it is very clear. First, I'm telling you the shortcuts. As it is very clear that the first wave, the yellow wave, is starting from the 0 and the blue wave is at the extreme position. It means the phase difference between them is 90 degree or pi by 2 radian. Because if one is at mean and one is at extreme at the same position, it means the phase difference between them is 90 degree. Okay, how to find the phase difference? Previously, I told you just simple example. Now I'm telling you the whole method. What is the equation that you can use? Phase difference is 2 pi small t over capital T when x-axis is time, where small t is the time difference between two identical adjacent points of the both waves, and capital T is the time period of the wave. Similarly, if x-axis is distance, then you can modify the formula as delta phi is 2 pi x over lambda, where x is the distance between identical adjacent points of the two waves. So using this equation, you can find the phase difference between any two waves. So let's apply this equation over here. Like the phase difference is 2 pi small t over capital T. Let's apply this. This is a wave. It's having point X and point Y, and they ask you to find the phase difference between point X and Y in terms of, it can be represented as n pi. So that's asking you what is the value of this n over there. So, well, first I can tell you the shortcut way. The shortcut way is, you have to listen very carefully. You have to divide the crest and trough into halves. And you know that each half is equal to, each half of the loop, each half of the crest or trough is equal to 90 degrees. So you have to count how many halves are there. 1, 2, 3, 4, 5, 6. So you will say it is 6 pi by 2. So it is actually 3 pi. So your answer is C. So the phase difference between X and Y is 3 pi. Let's move to next example. The frequency of a certain wave is 500 hertz and speed is 340 meter per second. What is the phase difference between the motion of the 2 points on the wave which are 0.17 meter apart? So 0.17 meter apart is what? It is X. And this is frequency and this is speed. So you have to find the phase difference. So the formula is, phase difference is 2 pi X over lambda. And actually they have given you the X, so you can simply put its value 0.17. In order to find lambda, you will use this equation, V equals F lambda, and lambda is V by F. V is 340 and F is 500. So you can find frequency from there. So it is 340 divided by 500, 0.68. So lambda is 0.68. So you will divide it with 0.68. So you can get the answer. 0.34 divided by 0.68. It is 0.5 pi. So the phase difference is 0.5 pi radian. Or pi by 2, and you know pi by 2 is 90 degrees. So, but pi by 2, like 0.5 pi is pi by 2 radian, so it is given in the option B. Okay, now here is the question which you will solve yourself. And you can solve it later. Like you have to tell about the phase difference between P and Q, then you have to find the speed. And this question we have already done in the previous lecture. The period of the vibration of the wave is T. The wave moves forward from the position shown in the figure at a time of 0.25 T. On figure, sketch the new position of wave. If you remember, we have done this in previous lecture, that how you can draw the wave position after a certain time. Okay, the next important topic is wave intensity. This is equally important as the phase difference. So what is wave intensity? It is energy transferred by a wave per unit time per unit area. Or it is power transferred by a wave per unit area. So wave intensity is intensity, you know, intensity means strength. So amount of light, amount of radiation. So if the amount of radiation is increasing, we say intensity is increasing. So based on its definition, there are two equations. Intensity is energy transferred by a wave per unit area per unit time, or intensity is power transferred by a wave per unit area, because you can clearly see from here that this energy over time is equal to power. So that's why replacing energy over time in that equation, you can write power. Now the unit is joule per meter square per second or watt per meter square. So let's say if this is the source and it is emitting some radiation, and you know that radiation when spreading, it spread through the form of a sphere, and that sphere is having an area of 4 pi r square. And as it is moving forward, it is spreading. That's why the intensity is going to decrease. So the first factor for the intensity, these are very important factors. That factor is r square. R is the distance of point from the source. This is inverse square law. It means that a wave's intensity decreases square times if the distance from the source is increasing. So that if the distance is twice, the intensity would be like this is R distance from source. So intensity was I, and if distance becomes 2R, intensity becomes I by 4. If distance becomes 3R, then intensity becomes I by 9 because I inversely proportional to R square. The next factor is intensity proportional to amplitude of the wave square, like I proportional to A square or I is K square, where K is the constant. And that's a very simple thing. Suppose there is a bird which is chirping and it's producing a sound wave of this amplitude, which is 2, and its intensity is I naught. Now, the bird got angry and it produces some louder sound. So let's say the amplitude goes to 6. So when the amplitude goes to 6, what's the intensity? So you will say that we have to use this relation I proportional to A square. So when the intensity was I naught, amplitude was 2. And what will be the new intensity if amplitude is 6? So how we will solve it? We will use the ratio method. One important thing, don't forget to take square because intensity proportional to A square. And then you need to multiply them, cross multiply them. So I into 2 square is 4 and I naught into 6 square is 36. So 4 9s are 36. So we say that the new intensity is 9 times the intensity of the previous sound wave. Okay, the last thing in it is the last factor, which is intensity directly proportional to frequency square. So let's say if a boy is talking, then his sound wave is going to the wall. And when a girl is talking, too many sound waves are going to the wall. And let's say they have same amplitude, but they have different frequency and they have same speed as well, because both the boy and the girl are talking in the same air, as the medium is same, so their speed is same and their amplitude is same. But the number of waves are different. The boy is producing less number of waves in 1 second and the girl is producing more number of waves in 1 second. It means the girl's frequency is higher than the boy frequency. So whenever you have to find the frequency or the intensity relation, you can use this expression that intensity is directly proportional to frequency square, or I is K F square. Boy frequency is F, intensity is I naught. So what if the girl's frequency is higher? So you have to find the intensity of the girl. Okay, hold on. Okay, so let's say if boy's frequency is 800 hertz and intensity was I naught. If girl's frequency is 2100 hertz, how much will be the girl's intensity in terms of I naught? So you can see that I proportional to F square. So what you can do is you will say that I proportional to F square. So boys intensity was I naught and frequency was 800 and then square. So girls intensity is X and frequency is 2100 square. So you cross multiply it to get the unknown value. So you will simply solve it to get your answer. So that will be the frequency for the girl. Is it clear? Only 3 factors are there. Like the first factor is the distance, the second one is the amplitude, and the third one is the frequency. Okay, let me just fetch some questions. Okay, so now what we have to do is we have to go to the next topic of waves, and we will solve the questions at the end. So this topic is known as Doppler's effect, Doppler's effect of sound waves. So this is a very interesting topic, Doppler effect. So for the Doppler effect, let me show you a video first. Yeah, this one. Okay, so now you have to watch this video carefully. Okay, it was a quick video, but I just have shown you this to give you some basic idea about the Doppler effect. So the Doppler effect is actually, it was actually investigated by the scientist Doppler, and it is very important phenomena. It is so important that like it is applicable in medical field. If you want to investigate the heart functioning, we use Doppler effect. If you want to investigate the heartbeat of the fetus inside mother's womb, Doppler effect is used. Then if you want to check the position of an aircraft, you have to use Doppler effect. On the highways, the speed cameras are being used by the patrolling police, so they use Doppler effect to detect or measure the speed of the vehicles. And the scientists have told us that our universe is still expanding after Big Bang. It is still expanding. So that happens only because of the Doppler effect. So Doppler effect is a very, very important phenomena in physics. Okay, so what is actually Doppler effect? It is the apparent change in frequency or wavelength of the waves due to relative movement between source and observer. It's the apparent change. It's not the permanent change, but it looks like that due to movement of source or observer, the frequency or the wavelength observed by the observer changes as it is really is. And the example is very simple. If you measure weight of something in air and you measure the weight of same thing while immersing it in liquid, both the weights will be different. In the liquid, the weight is coming out to be less than actual weight. So we say that the weight of the object in liquid is apparent weight because it is apparently being measured as less than that because of the upthrust force. As soon as you get the object out of the liquid, its weight become normal. So same is the Doppler effect. When the object is moving and it is producing some wave, so the observer who is observing that wave will feel the frequency and wavelength of the wave reaching him will be different as it is actually. So let me tell you the explanation. Let's say this is the source at the center, which is at rest. It is producing a wave of frequency fs, and the wave is traveling towards the observer with wave speed v. Observer A and B are there, and they will observe the frequency of the wave as f naught. So both observer A and B observe sound waves of the same frequency as produced by the source, like f naught is equal to fs. Why? Because the source and observers are static, they are not moving, so there will be no Doppler effect. But what is happening, and the same thing is over here, illustrated over here, that there is a source, ambulance, which is at rest. It is producing a sound wave of 800 hertz, and then there is observer, and he is going to observe the same frequency because neither of them is moving, so there will be no Doppler effect. So the wave wave which is produced by the source is having frequency fs. It is source frequency. And the observer observing the frequency, it is FO. FO is the frequency observed by observer. In this case, observed frequency is equal to source frequency because both the things are at rest. Okay, let's move on to the next thing. The next thing is source moving towards observer. So let's say if the source started moving towards the observer, so what would happen? Like, let's say this S is the source, which is producing wave of frequency fs, and wave is traveling with the speed v, and the source starts moving towards the observer with the speed vs. Okay, so as the source is moving towards the observer and it emits a second wave here, third wave here, so what will happen is that observer will observe the frequency of the wave as higher than the actual frequency because the source is moving towards the observer. So observer will be getting or receiving more number of waves every second than it is produced by the source. Let's look upon some of the terminology. V is the wave speed, Vs is the source speed, Fs is the frequency of the wave produced by the source, and F naught is the frequency of the wave observed by the observer. So if the source is moving towards observer, the observer will observe a high pitch sound, high pitch wave is observed. So the formula that you're going to use is F naught is equal to VFS over V minus VS. This is the formula which is given in the data booklet. So in the data booklet, you got this formula. F naught is VFS over V plus minus VS. So you got this formula. So you have to decide yourself that whether you are going to use a positive sign or a negative sign. So I have used a negative sign here because your F naught is going to increase. So F naught will increase only when denominator is a smaller number. So let's look upon here. This is the illustration of, this is example for the previous case. As the ambulance is moving towards this observer, so the lines, so the waves which are reaching that observer is bunching up. So that's why this observer is going to hear the higher pitch sound. And similarly, the waves which are reaching the observers behind the ambulance, they are spreading. So it means this observer is going to hear a low frequency wave. Actually, the frequency of the sound produced by this siren of the ambulance is same. It is not changed, it is same. But these observers observe the frequency different. Observer A observe a frequency less than actual frequency, and observer B observe the frequency higher than the actual frequency. So observer A is going to hear a low pitch sound, and observer B is going to hear a high pitch sound. So this change in frequency of the sound caused by the movement of the source is known as Doppler effect. So you can see from here, when the source is moving towards the stationary observer, like the eye is the stationary observer, you can see that the number of lines here, waves are here are bunching up. So it means frequency is increasing here. So this observer is going to observe high pitch sound. So if Fs was the actual frequency and F0 was observed, so we can clearly say that observed frequency is higher than the actual frequency. Okay, now the second case, we have to finish this topic. It will take another 5 minutes. So be there. Source moving away from the stationary observer. So a case can come that this source, which is producing waves, which is traveling with the speed v, so this source is moving opposite to the stationary observer with a speed vs. So as source is moving away, so less number of waves will be reaching observer per second as compared to waves produced per second. So that's why observer is going to observe a frequency that is less than the actual frequency. So a low pitch sound wave is going to be observed. So when a low pitch wave is there, of course, F0 should be less than Fs. So that's why a positive sign should be there. So you have to memorize these two equations. If the source is moving towards the observer, you have to use this formula to find anything which is given in the question, like a negative sign will be there. And if the same is moving away, you have to use the positive sign with the same formula. So you can look over here, if the source is moving away, and this is the observer, so less number of waves are reaching the observer. So it means that observer is observing a low pitch sound wave. So what are the calculations? So if the source and observer not moving, then observed frequency is equal to source frequency. If the source is moving towards the observer, then observer will hear a frequency greater than the source frequency. So you will use this formula. F0 is Vfs over V minus Vs. And if the source is moving away from the observer, you will use the same equation, but with a positive sign. And remember, what are these things? Fo is the observed frequency, Fs is the frequency as produced by the source, V is the wave speed, and Vs is the source speed. Okay, what are the applications of the Doppler effect? The first one is speed gun. Speed cameras used microwaves which reflect back from after hitting an incoming moving vehicle. The change or difference in the two frequencies that is emitted by the gun and received by the gun is used to determine the speed of the vehicle. So if you want to measure the speed of incoming vehicle, you will be using Doppler effect, and it is like as the vehicle is